Awesome.
Okay, so let's get started today. Today is Proximal Policy Optimization, otherwise known as PPO, and this is a deep reinforcement learning paper presented by Vlad and myself. So just some sources that we use to find materials for this paper. One is UC Berkeley's CS285 notes online. They have slides, recorded lectures, also OpenAI spinning up guide for reinforcement learning, and also Jonathan Hui's Medium article on policy gradients. So if you want to delve more into these later, feel free to use those sources. And some of our images are also from those sources.
Andrew, would you recommend the UC Berkeley course over the Stanford or the OpenAI course?
Great question. I didn't know OpenAI had a course, actually. I know DeepMind has a course.
Sorry, DeepMind, that's what I meant.
Okay, DeepMind. I actually think the DeepMind one is also pretty good, but the Berkeley one is like really good because that one is taught by Sergey Levin, and he's
Okay.
like one of the most famous people in RL.
Yep.
And he's just a really great lecturer. Like in the first lecture, like people clapped at the end. So really good analogies.
Okay, cool.
Yeah, great question. All right, so the agenda today, just a brief recap of reinforcement learning for people who are new to it. Then we'll talk about the basic vanilla policy gradients, and talk about what's wrong with being a vanilla person. And then we will go into the Proximal Policy Optimization paper. And now before we get started, just some context about why we chose PPO is because vanilla policy gradients, as hinted at this slide, there are many things wrong with it. So PPO improved policy gradients to the point where it was usable, I suppose, and is the foundation of a lot of other policy optimization techniques. This is an important paper to understand. All right, so first, the reinforcement learning recap. So in reinforcement learning, we of course have our world and we have our agent. Unlike classical machine learning, our agent is learning on the fly as it goes through the world. So the world has states, it responds with rewards, agent takes actions according to those states, and the path of action is called the trajectory. So an example of how trajectory might look is like this. If you have the robot in the first state T, it might take an action, goes to the next state T, and then another one, another one, another one. And that whole path is the trajectory. And at every single state, we're also getting some reward. It's a sub reward for that state, and then our total cumulative reward is summing up all those together. And just a rough map of the RL algorithms in deep reinforcement learning. There's model-free and model-based. PPO is a model-free version. Under model-free, there's typically policy gradients and Q-learning. And then under policy gradients, we're talking about today the vanilla one and the PPO one. All right, so let's get started on the vanilla policy gradients. So first thing I like to start with is the inputs and the outputs. So in this case, the input is going to be the state, and the output is going to be the probability of taking a specific action according to that state. Now, something similar you might have seen is deep Q-learning. This is also a model-free method where the input is the state and the output is a Q value of the actions. Like, what is the raw value of that? So what's the difference between that and the probability of taking an action? They look kind of similar. So the difference here is that because the top one is a probability, first is that we can sample an action via this probability as action given the state. And that inherently enables a little bit of exploration, because if you have some probability of doing this action, but not all the probability, you could sample some other actions, and you can just explore automatically using this method. Q values, on the other hand, if they want to do exploration, they must use some external tool, because the way Q value selects an action is that they just go with the max one, because these values don't actually represent probabilities. So they need some external tool like epsilon greedy. There are some other differences as well, such as how the gradient is estimated and how the networks are updated. Some behavioral differences. For example, Q-learning can store like a replay buffer. Policy gradients by themselves don't do that. But today we'll be focusing on policy gradients. So in a vanilla policy gradient, we are evaluating a single action. Actually, that might be wrong. Not evaluating a single action, evaluating a single state And the trajectory data is used once, because once you update your policy based on your trajectory, then your policy network is now different. So you can't guarantee the same trajectory again. And this comes in importance later. Well, so now for vanilla policy gradients, I'm going to talk about the trajectory and the gradient of the trajectory, and then how to update it. So the probability of a particular trajectory happening. Recall that a trajectory is a sequence of actions. So what's the probability that it'll go exactly on this path? Well, first, we start with the probability of the first state. That's just the probability that you wind up in any particular thing at the start. And then we have the probability that you're going to take a specific action given that state, according to your policy network. And then you have the probability that given that action you take, how will the world respond? What will the next state be? State t plus 1. So in order to get the probability of the whole trajectory, you simply do the, you multiply out all these together. Make sense so far? Cool. So now we're going to take the gradient of the trajectory. Before we just defined what the trajectory is, now we're going to take the gradient. So why are we taking the gradient? What does the gradient exactly mean? Again, basically when you take the gradient, it tells you how did the individual parts contribute to the whole. So in this case, the parts are the different actions and the parameters. And the whole is that trajectory that you went on and the total accumulated reward. So why do we want to know the gradient? It's because we want to know how each part of our policy network contributed to the whole reward, so that we know how each part should respond based on the reward that we get overall. So here again is our trajectory equation. How are we going to find the gradient of this? It looks a little bit complicated. If we're going to take the derivative of a bunch of sums, it's pretty easy, because for partial derivatives, if everything else will fall away in the sum. But in this case, we don't have sums. In this case, we have a bunch of products. And if you remember from calculus a long time ago, if you do the product rule, you have to do like, it's a lot of expansion there. So that's kind of annoying. So one way we can do this a lot easier is to use the log trick. And the log trick is just that the log of products, log of m times n, is equal to the sum of those products. So log of m plus log of n. And this will make differentiation a lot easier, because the derivative of sums is very easy. So in that case, the gradient of this trajectory is roughly summing up all of these logs of the action given the state. And this is a simplified explanation, by the way. There's a more complex explanation which you can find on the Berkeley source. Any questions so far? Okay.
Where does the P of S of 1 go in the gradient?
That's a good question. So P S of 1 and then P S of ST plus 1 ST AT, these ones actually don't depend on our parameters theta. They're kind of just,
Yeah, okay.
Yeah. So because they're independent, that means it's not part of the gradient. Good question. Yeah.
I have a question.
Yeah.
So earlier on, you talked about model-based and model-free algorithms.
Yes.
What is the difference?
That's also a good question. So when we say model, let's see if we can find that slide. Here we go. Yeah, model-free, model-based. I have this kind of cloud here. So when we say model, that means the agent is learning a model of the world. So it's basically learning the probability, like if I take a particular action, what's going to be the next state. It's a model of the world. And this is different from model free, because in model free, we're not learning a model. We're simply updating what we do without really knowing what's going to happen next.
Okay.
So, yeah, an analogy of this is like, for us, when we do planning, we kind of have a model of how the world is going to respond to doing things. Like if we study for a test, we have a model of the world that we're going to do better because we studied for the test. Model free is kind of like a reflex. So like, if you're falling, you don't really think about too much the model of your physics that you're following. Like if you step out, you're gonna stop it, right? It's kind of like just a reflex. You just do it. That's model free.
Mm-hmm.
Yeah.
Okay,
Very
that
good
makes
question.
sense.
Mm-hmm. Any other questions?
Just to comment on that, we were looking at AlphaZero for previous paper review. That's the model-based algorithm. And also, I think it's not necessarily that you need to learn the model. It's more like you have some sort of way to just generate the next state. Maybe the hard-coded model.
Right. I think, as far as I understand, I might be mistaken, but I think model-based essentially roughly means that you have some sense of an MDP defined. Correct me if I'm wrong.
Some sense of MDP defined. So like
MDP, like that you
Markov decision process.
Yes, so that you're using states and state transitions. Not necessarily, actually, because
Okay.
you may still use the state, and the state might have the meaningful information for you to behave in the long term, but you don't model the next states. So model-based will try to generate the next state, and I think it's related not to MDP, but to, let's see, what's the graph way of picking. Well, basically, it allows you to construct graphs for your decisions.
When you say graphs of decisions, isn't that? I mean, I when you say that, I just think of an MDP because it does have a graph-like structure.
Yeah. I think there was a different definition
For sure, sure.
The way how you call that. I don't remember what's that.
Sure, no worries. That just means we both need to look into it more.
Yeah.
By the way, there's a difference between Markovian and MDP. To be Markovian means that everything you need to know about the world you can understand in the current state. MDP is like a specific decision-making process based on Markovian environments, I think. Just FYI.
Right, like a current state is representative of the history of all states.
Yes, that's Markovian.
And so aren't MDPs Markovian in nature?
MDP,
yeah.
I believe that was a part of the, at least in the little coursework I did, I believe that was part of the definition for an MDP.
Right.
Yeah, that should be.
Cool, something to look at more later.
Yeah.
Anyways. Okay, and
Monte Carlo. I remember that.
Monte Carlo.
For the graph for the decision formulation. That's what you use with model-based. Yeah, sorry.
Cool, okay. Cool. All right, so now that we have the gradient of this trajectory, that's not quite it though, right? Because we're trying to evaluate our model based on the reward, not just on what trajectory we took. I mean, they're kind of related, but how exactly are they related? So remember that for our trajectory, we also get rewards at each state. So like we're going to have a reward at time 0, as we go on. And then that relates to our overall objective because our overall objective is the sum of the rewards. So we can relate this to our trajectory by just attaching the reward at that state to the gradient there, and that becomes the gradient of our overall objective. And when we update our parameters theta, all we have to do is do gradient ascent. So we start with what theta was, and then we take a step in the direction to maximize that objective. So in effect, this has the effect of increasing the probability of good trajectories, because a good trajectory means that you have a high reward. So then you have a high reward, you have a high this thing. So then big positive this thing plus this thing goes up. And it'll decrease bad trajectories. So bad trajectories, if it's negative, then it will go down. So cool, that sounds pretty straightforward, I hope. But what's wrong with vanilla policy gradients? Because it turns out that there's a lot of issues with this formulation.
There are some, yeah. So first of all, if you look at raw rewards, what you will see that often for every step, for every transition, you will get some non-zero reward. Maybe you will get a low one, like 2, for example. And it doesn't really show you the direction of whether it's a bad action or not. So you will scale your gradients. You will make the step towards somewhat right direction, because actions that are better will be amplified more than actions that have lower reward. However, it doesn't really tell you which actions are bad or whether you should take the step to the other direction if you took the action that's worse than you usually take. And so there is a one solution that we can use for that, even for vanilla gradients, which is looking at some baseline and just subtracting every reward, just subtracting this baseline from every reward that we have. So this way, you have some expectation of the value reward that you usually get with this policy. So you have the sense whether the action you've taken is actually better compared to the actions you took usually, or is it worse? And what it allows you to do, basically, to take the gradient in the direction that makes sense. So if it is less than you would usually get, your value will be negative, and so you will take the step in a negative direction. And in the positive, it is the positive. We're thinking about the example that you could imagine trying out a new meal, and you have good expectations over it. It looks very good, delicious, but in fact it's not really that good, and so your advantage there is sort of less. On the other hand, if you're trying out something that you don't have very well expectations, or your expectations are just neutral, mild, then if it tastes really good, then you will like it and you will want to try it again. That's the basic intuition behind the advantage here.
I had a question. So is this kind of like subtracting the mean reward from each reward?
Mm-hmm.
So
Yeah.
that you
Yes, actually, you would subtract the value for that state you're in. So that's not necessarily the average reward in the whole trajectory, but you could actually use average reward from the whole trajectory as your estimate, or from all trajectories under this policy. You could do that.
Cool.
Right. And can we clarify how the value is calculated for this state? Is the value the sum of the rewards from that state onwards?
Yes. Also, what you're saying is that the whole reward is not just, even without the baseline, the whole reward that you will look at is not necessarily just a reward for taking the action in a certain state, but it's actually this reward and every reward that you've received after taking that action, because your action influences what will happen in the future. So you're not just interested in one thing, you're interested in all of that. Just one detail that you might be interested in.
Cool, good.
Thanks for that note.
Oh, yeah. Oh yeah, go ahead.
Yeah, this is how we show how we refer to reward. Just noting it as advantage here in our policy gradients.
Yep, just replace.
We can refer to it as RSA or SSA of data.
Right. Cool. So that was problem 1, and we addressed problem 1 by using advantage instead. There's another problem though, problem 2, which is over-optimization. So typically in deep learning, we have our data already, right? Our data is predefined, and then we just loop over the data and optimize on it. But in reinforcement learning, for policy gradients specifically, the current trajectory that we're on, we only get that data once, because once we update our network, it affects the data that we get next. Right? So we can't guarantee that we're going to get this trajectory again. So how can we use this trajectory as much as possible? So naively, we can try and optimize as much as possible on the current trajectory. We just keep updating over and over and over again so that we get down to this global minimum. I mean, that seems really nice, but there's a problem with this because this is essentially overfitting. If we update too far, we could get stuck in a really bad situation. So let's take an example. Say that you have a little baby, and the baby is learning to walk. So the baby is standing on its 2 legs, and it moves 1 leg and it falls over. It's definitely not walking. So because moving 1 leg had it fall over, then it learns, oh, I should never move that leg again. But then if it never moves that leg again, it can never discover that it can keep that your legs are actually really essential to walking, right? And then the next trajectory would become very poor because the baby's no longer moving its legs. So that sucks. So another example of this, Vlad has this picture of half dome. If you take too big of a step, you're up here, and then bam, you fall over. Then you're just stuck down here, you can't get back up. So how can we avoid these huge updates? It turns out that a really simple idea, or maybe not simple, but you can apply a penalty to the gradient so that you don't take too big of a step. It's kind of like regularization. And actually, we're going to talk about gradient clipping in the PPO paper. So here's a proximal policy optimization presented by Vlad.
Yep. So this is the, if you compare the regular objective that we have for policy gradients, the objectives lower are what we use, what policy optimization, proximal policy optimization paper proposes. So there are 2 things that they propose. First of all, the way that you can combat this state when you get the gradient that's too much, that's huge, and that can break your model. There's 2 things that you can do. You can either penalize the update, the gradient somehow, depending on how far you want to go, or you can apply the clipping. So just clip this gradient and not allow it to be more than a certain value if it's after it reaches certain value. Basically, this is how the clipping will work. This R ratio here, it basically represents how much more likely is it to take this action under the new policy than it is under the old policy. So R bigger than 1 here would mean that taking this action under the new policy is more likely than it was before, and otherwise. So here, just a second, we have a so for example, if you have the new action, the new policy tells you that making this action is more likely under the new policy. And it also has a positive advantage. This will be what we see on the left graph. If it is really a much better action, then you don't want to overshoot and to make your gradient too big, because this will happen eventually. And if you don't clip the gradient, you will just end up off the hill, you will just fall off. So instead, you will make the step that's bounded with some value. On the other hand, if the advantage is negative, so the action that you've taken is worse than you usually expect, then you sort of want to behave in a different way. You want to have your update bigger if it happens to occur, and so if it is more likely than that you will take the action that resulted in a negative reward, then you will make a bigger step to negate that. And if that action is negative, then you don't really care, but you can make some step regardless. So the most important part is on the left here, because this assures that we don't make the step that's too big, essentially. Does that make sense? How do you feel about that?
That makes sense. I just found something kind of weird about this graph. So on the right hand side, when the advantage is negative, it seems that the more negative values are kept, but the less negative values are clipped off. And I thought the point was to avoid extreme gradient changes.
Wait, say again,
Yes.
the more negative values are kept, right? And the less negative values are clipped off. Okay.
Yeah, so it is sort of weird because the values that are less than 1, they will occur less. That there's a smaller probability that they will occur. So why would you penalize them at the same rate as those that will occur a bit more, for example? Why wouldn't you just keep the straight line to the 0 here, for example?
Yeah.
What we've
or potentially
Mike,
clip it after, like clip it on the right hand side. You know what I mean? Instead of the left hand side of the.
Yeah. So let me take a step. So yeah, this graph on the right hand side is actually kind of tricky for us to understand as well. But let's take a look at the right hand side first. So advantage is negative. So what we did was actually a lot worse than we thought. So if R is big, that means we're doing that action more. The action is more likely, but it was actually bad. So because that action was bad, and before we're doing it more, we actually want to do it less. So we want to try and get closer to what we were doing before, pi theta old. Does that part make sense?
so you can't get the big gradient there.
Yeah.
It's just it sounds a bit maybe if you think about it as that should be somewhat symmetrical with the left side, then it doesn't make sense because the whole thing was the whole idea was to avoid using big gradients, right? So that we don't fall anywhere. And here we sort of are doing the opposite thing. But apparently it, I would say, I'm not sure, I'm not getting the whole picture, but my understanding is that it works because maybe you're finding yourself in a place with such gradient less times, I guess.
Awesome. Thank you.
Right. I think the idea is less of having smaller gradients, but more of keeping closer to what you were doing in the past, like not straying too far what you were doing in the past. That's why if what we were doing in the past, sorry, if our new stuff is very, very different and that turned out to be very bad, that's why we want to shoot more this way. Versus on the left side, if it turns out that what we're doing really bad, then we also don't want to stray too far from what we were doing before, because if we just multiply by a very small number over and over, it's just going to trend towards 0. So to prevent that from happening, from making the action not happening ever again, we instead clip it.
So it's kind of like preventing the gradients from exploding or vanishing.
Yes, well, preventing from getting too far from our previous policy.
Okay, yeah. Awesome.
Yeah, this is like on the left, this is like the baby. This is preventing the baby from, or if this was not clipped, then if the baby took a step and he fell, then it would never happen again. But making this clipped means that he'll still do it a little bit. Then this right side is like the baby fell down the stairs and that was really bad. So we should not do that ever again. Yeah. Okay. Oh.
Right. So they also propose a different approach, not to clip, but to use scale divergence, which is basically the difference, numerical difference between the old and the new policy. They just will subtract that value that represents the difference between the policy. And that's just a quick overview that they're doing that. And they have found out that this approach doesn't work as well as the clipping. And this is something that they were trying with TRPO before, which is heavily relies on KO divergence and more complicated algorithms for optimizing this way of not deviating from the original policy too much. It turns out that clipping, as simple as it is, works better than most of those complicated, complex algorithms. And we have a small demo of what PPO can do. This is actually by DeepMind. They use some sort of parallelized PPO algorithm to learn locomotions. Yeah.
Yeah, so like we said before, PPO is the basis for a lot of modern policy grading algorithms. And actually, Gaurav is using a little bit of clipped PPO at his internship right now.
Yeah, so I could talk about that a little bit. So basically, at my work, the problem we're trying to solve is trying to see if we can simulate a satellite in trajectory and see if we can teach another satellite to follow this satellite that's already in orbit through reinforcement learning. So obviously, we're not working in the domain of space yet. We're kind of working in simulation for right now. And so we're basically using clip PPO to train the client robot to follow the target robot. So yeah.
Cool.
Any questions on that?
How did it perform?
Why did you guys decide on clip PPO?
So clipped PPO was not our decision. It was more so the kind of the code that was given to us. It doesn't perform. So it performs well when the target is stationary. So for example, if you have your robot that's stationary, then it performs decently well. But once you start moving it, it's not that good. Also, the reward function has some weird behaviors. So currently testing to use DDQN. That I've seen a paper where that seems to have better kind of better results in terms of tracking moving objects. So yeah, that was Sam's question. What was your question, Andrew?
Oh, I didn't have a question. I just wanted to comment. That's good insight because wouldn't know that clipped PPO is not doing well on moving trajectories otherwise if you hadn't said so.
I mean that's empirical. That's my empirical thought.
Right.
Through our testing, I didn't find through our testing, we wasn't the reward function was behaving kind of weird. So we're gonna test other algorithms as well.
Also, what's the input to the model, the agent?
So well, like what is the environment? Is that your question?
No, just like what does the agent observe? Like what's the like what can it see? What's its observation? Like what is it making its actions based off of?
Yeah, so each, these are like Turtlebot 3s. I don't know if you've ever heard of them. They're basically has a camera and a LiDAR sensor. So that's how that's its kind of sensory input to the world.
I see. Cool.
And the environment is simulated in Gazebo. Gazebo is, so there is a programming language slash, like the way you code robots in simulation and kind of transfer it to real world is through ROS. It's not, it stands for robot operating system, not necessarily an operating system, more of like a middleware to communicate between several different packages. So ROS has a simulation tool called Gazebo. So we simulate and train in Gazebo for the robot.
Cool. Thanks for sharing, Gaurav.
Yeah, thank you.
Yeah. So that's it for our presentation today. Thanks very much for coming. Open to questions if there's any more. Otherwise, we'll see you guys next week.
Just as a announcement, next week will be our last meeting before the school year.
Whoa, already?
Yeah. So we will probably still continue the Friday meetings, but more information coming your way soon.
Okay, great. Thank you, Gaurav. See you guys later.
Thanks, everyone. Great job, Vlad. Thank you. Great job, Andrew.
Thank you, Gaurav. Bye.
Bye, everyone.
See you guys.
Bye.
Bye.
See you.